first, let's see. Yeah. All right, first we're going to be talking about energy in this chapter, work and energy. There are a number of different types of energy. There's the energy that's associated with motion, and then there's the energy that's associated with the potential for motion. So for example, if I throw this eraser, it has energy because it's moving. And then also if I place this eraser within a force field, or the gravitational field in this case, then it has the potential for motion, right? Because if I let it go, what's going to happen to it? All right, fall. Let's throw up. It has the potential for motion. And we'll talk about a number of different types of potential energy, but primarily we'll look at gravitational potential energy. That is, if I have something that's affected by gravity, then it has the potential for motion. But obviously there are other types of potential motion, like electric potential motion, or electric potential energy rather, chemical potential energy, a number of different others. So let's see, collectively these are all called mechanical energy. And this is in contrast to other types of energy, thermal, nuclear, electrical, which we'll talk about later in the course, at least the thermal, and then the electrical we'll talk about next semester. All right, so before we move on, I want to go over the dot product. Has anybody ever seen a dot product before? I don't think y'all really get to that until Calc 3, but you might have seen it in high school. We'll do a number of things from vector calculus. One is the dot product, and then we'll also do the cross product. Again, probably you'll never see it in calculus, but it's pretty important when we're talking about work and energy to calculate the work due to a vector that's a force. And so I'll show you what to do. It's not that difficult. So the dot product is also called the scalar product. It's the product of the magnitude of one vector with a component of the second vector, and the component of the second vector is in the same direction as the first vector. So for example, let's say that I have these two vectors. I have a vector A pointing in this direction. Well, let's just say that its magnitude is, I don't know, 4 units long. It's 4 units long. And then I have a vector B, and it's pointing up in this direction. And we'll say that its magnitude is let's just say it's 1 unit long. And let's say that this angle, just for example, is equal to 60 degrees. All right, so I can find the magnitude of the x component of this vector just by saying b cosine theta. That's going to be 1 cosine of 60, and that's going to equal to 1/2. Because cosine of 60 is 1/2. And so the dot product of A dot B would equal to 4 times 1/2, which is just equal to 2. So it's just the magnitude of this first vector times the component of the second vector that's in the same direction as the first vector. All right. Now, if I were to rewrite this a little bit differently, just sort of showing you graphically, let's say instead that the vector A was in this direction, and then my vector B was in this direction, then the component that I would take would be that component for B. So it's not necessarily the x component that we're looking at, it's the component of the vector that's in the same direction as the first vector. Or whatever, it doesn't really matter. Yeah.
So could you use B if you use the opposite? Could you do like other way? Like use the
could, but it would work out the same way. I'll show you all. So you're not really going to do it graphically like this. I just wanted to show you all that it's the first vector times the component of the second vector. Or vice versa, it can be the second vector times the component of the first vector. But mathematically, it doesn't matter. It's going to come out. All right, so the way to find this is, I would say, I'm going to go to the next page, that A dot B is equal to the magnitude of the first vector times the magnitude of the second vector times the angle between those two vectors. All right, so when the vectors are in vector notation, you just multiply them out with the components of the vector, just with FOIL. I'll do an example of this in just a second. But you just need to remember that when you're multiplying these out, that these things are true for all of my unit vectors, right? Because I dot I, remember I has a magnitude equal to 1, and that's the same true for j and k. And so when I multiply them out for I dot I have 1 times 1, and then the angle between those is 0 degrees. So I dot I, the dot product of I and I, is just equal to 1, because cosine of 0 is 1. But what is cosine of 90? It's equal to 0. So when I do I dot j, for example, for any two vectors that are perpendicular to one another, then they're equal to 0. Can you explain that in a graphical sense, why that is? That why a vector, the dot product of a vector with a vector that's perpendicular to it, why is that dot product equal to 0?
Because there's no, go straight up on perpendicular. There's
No
no component of the second.
Right, right. So there's no component of the second vector that's in the same direction as the first vector. So it would be times 0. Right. So anytime you have two perpendicular vectors, their dot product is 0. Let me do an example for you. And we'll do some examples in the class as well. So let's say, for example, I have these two vectors, A dot B, and I want to find the dot product. So A dot B is equal to 2i plus 3j dotted with 1i minus 2k. Why don't y'all try that out? What you're going to do is just multiply it out using FOIL, first, outer, inner, last. And on each of those, you'll, for example, with the first, you'll get 2 times 1, I dot I. So for your first term, I get 2 times 1, I dot I. And since I dot I is equal to 1, then that first term is just equal to 2. And then you do your outer, then you do your inner, and then you do your last. But then some of those cancel out.
Where are you getting your K from?
Oh, that was just my vector B. So see, my vector B here is 1i minus 2k. I'm just giving you two vectors. Right, they don't really mean anything right now, but we'll use them for a physical sense. You gonna drop something?
No, I dropped my eraser.
I bet you gotta watch, right? It's an old white eraser. Like here it is.
I got it.
We might know the answer to this. The spot product. What is it? You do know the answer? What is it?
Oh, no, I don't.
Okay, well, let's see. So first is 2i times 1i. The outer is 2i times negative 2k. What's that equal to? Okay, but what is I dot k is equal to 0. Right, so outer is 0. Inner is 3j times 1i. What's that equal to? Is 0. The dot product of j dot I is equal to 0 because they're perpendicular or orthogonal. And then 3 times 2 is negative 6, j dot k. So that's equal to what? 0. So what's the answer? It's just equal to 2. Let me write this out, though, so we can just see. That's my first, my outer is 2 times negative 2 times I dot k. My inner is 3 times 1 times j dot I. And then my last is 3 times negative 2 times j dot k. Alright, so some of these go to 0, most of them do. I dot k is 0, j dot I is 0, and j dot k is 0. So this is equal to 2 times 1. I dot I is equal to 1, so it's just equal to 2. Alright? This is a scalar quantity. It has no direction information. In fact, that's why we call the dot product also the scalar product. We'll get into another vector product later, which is called the cross product, which is going to be called the vector product. All right? You can do dot products? Okay. We'll do some more practice. They'll definitely be on the quiz. You'll have to do a dot product on the quiz, for sure. All right? It won't be terribly complicated. Something simple like this. You need to know how to implement that for physical reasons. All right, can I go down from here? Is that something new? You've never seen a dot product before, right? So that's exciting, right? You learn something new. Like they say you should learn something new every day. So there you go. Learn how to do dot product. All right. Now this becomes relevant when we're looking at work, because work is going to be the dot product between two vectors. Work is done when a force is applied over some distance. And to calculate the work, we must multiply the magnitude of the force
The air conditioning or rain?
what, Scott?
The air conditioning or rain?
I think that's it. I don't know. Is it raining outside? You know, it rained a little bit on me this morning. The magnitude of force times the component of the displacement, which is in the same direction as the force. All right, and this is the definition of what? Well, it's the definition of work, but it's the definition of what kind of product? It's the dot product. So that's why we use the dot product in this particular case, because it takes the magnitude of one vector and multiplies it times the component of another vector that's in the same direction. Yeah, God bless you. All right, so I can calculate my work is equal to F dot D, the vector F dot D. However, we can also define this. See, I don't know if I wrote this up here. Let me go up for just a second. I'll come right back. I did not. I didn't say it explicitly. But we can also calculate the dot product is just going to be F times D times the cosine of the angle between them. So if I have two vectors, A dot B, I can find the dot product also. I can do it that way where if I have them in vector notation, I can multiply them out and do the whole I dot I as 1, I dot J as 0 kind of bit. Or if I just know the magnitudes of the vectors, I can say that it's that. The vector A times the vector B, or the magnitude of A times the magnitude of B, times the cosine of the angle between those two vectors. All right, so that would look like this. I would have a vector A, a vector B, and then the angle theta here between them. So in that way, sort of getting back, I think Rob maybe asked the question, are you taking the component of A or are you taking the component of B? It doesn't really matter because that cosine angle will either give you the vector of A in this direction or it will give you the vector B in that direction, in which either way the dot product is going to work out the same. All right? So this is another definition for the dot product, and we'll use that as well. And that works over into the definition for work. If I want to find the work, it's F times D times cosine theta. So say, for example, I have a box or whatever, and I want to apply a force to it. I say that this desk is the box. I apply a force that's in this direction. So I'm not pulling straight like this, but instead I'm pulling at an angle, at some angle theta, like in the figure here, where I have a force that's applied up and in the direction that I'm pulling it. Only a component of that force is actually doing work, because the component of the force is not causing any motion at all. Which component of the force is not causing any motion?
The Y.
The Y component, right? Because the Y component, which is pulling up on the desk, isn't causing it to move. Right? So it's doing no work. Remember, work has to cause motion. So the X component of the force is causing motion, and the X component of the force is causing motion in the X direction. So when we find the work, we'll multiply this component of the force times this displacement in order to find the amount of work that's being done. Is that clear so far? Okay. We'll do some examples and it'll be more clear. Now, if F and D are parallel, that means that theta equals 0. Then we have FD cosine theta. That just simplifies to just F times D, because cosine of 0 is 1. And so, for example, if I have something like this, where I have a force and a displacement, then my work is just F times delta X. All right, now the unit that we use for work, and we'll also use this for energy, because they measure basically the same thing, is a joule. It's somebody's name, scientist from 19th century, I think, 1800s.
Aren't they all technically someone's name?
No, I mean, kilogram isn't somebody's name, right? But a lot of units are. I guess, like, that's sort of the pinnacle of your career is to have a...
Lost.
What's that?
It made it because it originated as Graham, and they just
Oh, yeah, it did,
out
didn't it?
and they
Yeah, I
made
forgot.
someone's name.
Well, seconds. That's not somebody's name, right? There are lots of units that aren't people's names.
Hopefully. Because I hate to think the kid name. I look at seconds.
All right. Anyway, so the unit for work is the joule. We can break this into its SI units. All right, it's going to be a Newton times a meter. But of course, a Newton isn't just a Newton. It's actually a kilogram meter per second squared times meters. So the units for a joule, the basic SI units are kilogram meter squared per second squared. All right, so these are equivalent. I certainly don't memorize the basic SI units, but just be able to take the formula and break it down into its basic SI units. You could see that as a multiple choice question. Not likely, but you could see it. All right, that's useful, especially if you're doing dimensional analysis on your equations, to see if you're getting the equation correct. All right, so I've already said this, but if there's no motion in the direction of the force, then there's no work being done. So I can sit here and pull all day on this desk, pulling it up, but if I never cause it to move in the y direction, then it's not doing any work on the desk. All right, so if there's no displacement in the direction of force, there's no work done by the force. So for example, if I do pick up the desk, and then I move around at a constant velocity, this isn't a constant velocity, but imagine if I were moving at a constant velocity, what would the work being done on the desk?
Both up and.
What's that?
Both up and.
Okay, well, I pick it up, and then I keep it there. Yeah, and then if I move around at a constant velocity, that means that there's no acceleration in the direction, in either direction. So there's going to be no work done. Because if I have no acceleration, I'm exerting no forces. I understand what you're saying, Chris, and technically you're correct. When I pick it up, I do work in the y direction. Or I do work as I move it in the y direction. All right, let's do some examples. What's that? Somebody say something? Alright. Alright, so dissipative forces such as friction also do work, but they generally do negative work. But remember, work is a scalar quantity. So the negative doesn't refer to direction, because it has no direction. Instead, the negative means that it's taking away energy, something that we'll call energy. So negative implies the force is taking away energy. And we'll sort of formalize that later, mathematically. Right. The reason it comes out negative, though, is because the force and the displacement are in opposite directions. And so if I have a force in one direction and a displacement in another direction, if I do work is equal to FD cosine theta, that's going to be FD cosine of 180, which is -1. So it's going to be negative F times D. And so it just works out to be a negative work, but it doesn't imply the direction. All right, you want to do an example? I want y'all to try it on your own for just a moment. The next page, can I go down from here? Got just a second. Were there any big events from the weekend? No? My wife was away. I was, what do they say? Batching it, as they say. Did I tell y'all this? She was going away.
I heard we won the football game.
Huh? Yeah, man. I heard it was really great. I didn't get to go. But, well, Catherine, you were there, right?
I was at the tailgate thing, but I didn't go into the stadium.
Oh, but you were in the homecoming court, weren't you?
No. I
saw your picture somewhere.
I was in an animation, but I didn't think of it.
Oh, sorry. I would have noticed.
I think it was pretty busy anyway, so I don't think I'm kind of glad that I didn't have something.
Really? I'm not. I think you're really great. All right. All right, so force acts on a particle, which is initially at rest. There's the force. The particle is initially at that position, and then after 2 seconds, it is at that next position. I just want you to do part A right now. How much work has been done by the force? And then I'll help you with part B, because we haven't defined power yet. First step will be to find the displacement, which remember is the difference between the final and initial, and then you just need to do the dot product to find the work. So I get this for your displacement, 3 plus 4j, 3i plus 4j. Yeah. What did y'all get for the work? Huh? Working on it. Okay, I'm sorry.
21?
No, it's not 21. But it's 25, right? But y'all keep going. Once you get the hang of this, you'll see that you don't need to write out all the terms, because most of the terms go to 0.
Oh, yeah. Am I getting that? Multiplication skills. 4 times 4 is 16. Oh. Need threes.
All right, so what did you, okay? 25? Yeah, so if I find my work, it's equal to F dot D. That's going to be 3i plus 4j, dotted with 3i plus 4j. All right, but I know that it's only the first and last terms that are relevant, because the inner terms and the outer terms are j dot I and I dot j, inner are j dot I, outer is I dot j. So those go to 0. So I just write my first and last terms. That's 3 times 3, I dot I. That's just equal to 9. And then 4 times 4, j dot j. That's equal to 16. So it's 25 joules. All right, so that's for part A. It's just doing the dot product. For part B, we wanted to find the power. Let me go ahead and define power right now. We'll see it again a little bit later. But it's just the work or the energy per unit time. All right, so it's going to be 25 joules. Oh, what is it? It's just the work divided by the time. Just take a second to do that. All right, so it's equal to what? What is it? Right, or just 13, what we'll call watts. We'll define this later. It's joules per second. And then C, I want to find the mass of the particle. Right. I give a hint here that the x displacement equals 1/2 axt squared. So from that, you can calculate the acceleration in the x direction, because I know what my x displacement is. That's 3 meters. And I know what my time is. And then once you know the acceleration in the x direction, you know the force in the x direction, so you can find the mass. Let me try that out. mass, yep. Not yet. Connor, you got the mass? Do you have the mass? Not yet. What do you have? 20? Close. No. He's got it. Scott, you got it? Two. Right. So here I can calculate my acceleration. This is just from our kinematics equation. Why did I leave off the v naught term here? The kinematics equation is actually v naught t plus 1/2 at squared. Why is the v naught not there? Why is it, Brittany? Right, yes. I said that it was initially at rest. So v naught in the x and the y direction is 0. And then from that, you know the x displacement, because I'm going from 3.25 from 0.25. So my x displacement is 3. And so I can solve then for the acceleration and find that it's 1.5 meters per second squared. And then I know that the force in the x direction is 3 newtons. And so that's equal to m times my acceleration in the x direction. And so m has to equal 2 kilograms, the mass. So that's the answer to that part. All right. Let me show you part D. Now there's a more difficult way to do part D where you solve the kinematics equations. And then in part D you could find the acceleration in the x and the y directions and then solve for the final velocity. I think y'all could maybe do that, right? If you were pushed, like if somebody's really... What's that? You couldn't. Oh yeah, you could do it. But there's an easier way to do this that we'll use this approach. Something called the WorkEnergy Theorem. We'll get to this in a bit, but I'm going to go and introduce it here. The WorkEnergy Theorem. And this just says that if you do work on an object, then you increase its energy. Alright, and we can calculate the energy of an object, the kinetic energy, which is the energy due to motion, in this way. And we'll get to this a little bit later, but this part of the problem involves it. It's equal to 1/2 mv squared. 1/2 times the mass times the speed squared. So I can say then, I can take the amount of work, which is equal to 25 joules, and set that equal to the amount of kinetic energy. So I have 25 joules equals 1/2 mv squared, and then I can solve for v. So v is the square root of 25 divided by 1/2 of our mass, which is 2 kilograms, and that of course is equal to 5. So that's the magnitude of the velocity. Yeah, Andrew?
What's after W equals what?
Work equals kinetic energy.
Alright.
We'll get to that again. We haven't seen that yet, but we'll get to that in this chapter, the WorkEnergy Theorem. But it was applied here, so I wanted to show y'all. All right. That's a good test question, a good quiz question. You will have to do a dot product. I'll show you some other examples of types of questions you should be prepared for. All right. Let's see what we got next. Can I go down from here, guys? Yeah. I'll post this recording. I am recording now, so yes, I'm recording now. All right.
How'd you hope?
You think we could do these and like y'all could imagine that the answers aren't on the page? You see the answers are on the page. Yeah. There was a faculty member in our department actually, and one time he or she made up an exam, and when they were making up the exam, they bolded all the right answers. You do that sometimes, right? Just so, like when you're working through the exam, you make sure that you have the key correct and all that business. But this person forgot to change those answers back, and so when they handed out the exam, all the correct answers were bolded, and nobody said anything, right? And the sad thing is that like people still did poorly on the exam.
Because
They thought it was a trick,
either
yeah.
assumed it was a trick or they didn't notice the difference.
Right, yeah.
But they were just so tired from studying.
Right, yeah. So, anyway, I'll just step through them. We won't do them as quick.
You should do that. You should decide to an experiment like that.
All right. Yeah, we should do that.
Psychological.
Maybe I could just, like on the free response, I could like work them out, but then just sort of have it like as a watermark on the page. Just very faint ink on the page. All right, so
Holding their paper up.
it says that which force does no work. Option A is a force doing no work. Now each of these figures are moving to the left. Why is it option A that's doing no work?
Because it has no point in that direction.
Right, because the force and the displacement are perpendicular to one another, or they're orthogonal to one another. Which force does negative work? All right, C does negative work. Why does it do negative work? Right, because that cosine of the angle is cosine of 180, and the cosine of 180 is -1. Or they're in opposite directions. They're anti-parallel. Which force does positive work? I have B and D. Why is that? They're in the same direction. Now for number D, for block D, is at some angle, but the component of the force, the x component of the force is in the same direction as the displacement, which is to the left. And which force does the most work? Why does this block do more work than this block?
Because energy is not being wasted, force is not being wasted to try and pick it up.
Right, yeah, so the component of the force in the direction of the displacement is greater. And as Scott said, which is correct, that you're not wasting energy by trying to pick it up.
My physics teacher and thing, he we didn't go as far into actually doing the dot thing. He kind of explained it to us. We're trying to push a block, a very, very heavy block along the thing. If you want to push, you have to get down and push equal to it, not push down,
Right.
Where you'd be creating more friction and stopping it.
Could you write out for B and C?
Mm-hmm. Yeah, so I'll write it out for all of them actually. The force that does no work is A, and mathematically we would say that this is F D cosine of 90, which is equal to 0, because my displacement here is perpendicular to my force. The force that does negative work is C. Remember, my displacement is in this direction, and so that angle is 180. So F D cosine of 180 is equal to negative FD. The force that does positive work is B and D. The displacement is in this direction. The displacement is in this direction. So they're both in the same direction. For this one, it'll be FD cosine of 0. Oh, excuse me, that's a 0. Which is just going to equal F times D, positive F times D. Over here, it's going to be, if this is my displacement, this is my angle, it's going to be FD cosine theta, but that's a positive value, because that angle is less than 90. And then the force that does the most work is this force, because the cosine of theta is 1, and that's its maximum value, is 1. Is that clear? Rob, did that answer your question?
Why is D, so D always goes to the left?
No, I just did in this figure. So obviously we have other forces that acting on the
So
object.
it's just blocks moving to the left. Okay,
Yeah.
so that's why this placement is so refused to be done.
We'll see some similar questions on the clicker questions coming up. Not today, next time. All right. I go down from here. Just just a couple more things, I'll give your quizzes back. All right, when you lift an object, do you do positive or negative work? And does gravity do positive or negative work? So if I pick up this object, if I lift it, am I doing positive or negative work? I'm doing positive work, right. We can actually think about the WorkEnergy Theorem. I'm increasing its kinetic energy and making it move, and so that means I'm doing positive work. Remember, the positive doesn't refer to direction. It refers to, am I giving it energy or taking away energy? Or what about gravity? If I'm moving it, if I'm picking this up, what is the gravitational force doing? Is that positive or negative work?
It's negative.
It's negative, right? It's the opposite the direction of motion. So if I lift an object, I have to exert a force in this direction, and the displacement is in that direction, and so that's going to be positive work because they're in the same direction. However, the gravitational force is in that direction, so it's doing negative work. So it's actually taking energy away from the object if it's moving upwards. All right? Let's pick back up with this next time. I want to give your quizzes back. And actually, I want you to take out a sheet of paper, and then while you're doing that, I hand your quizzes out back. Just a blank sheet of paper. I like to do midterm assessments. So you'll do an assessment at the end of the course where, you do all the bubbles and all that jazz. But it won't really change the course for you anyway, or it might for next semester. But I always like to do just sort of a midterm assessment to see how we stand in the course. So on a blank sheet of paper without your name, do you need a sheet? Oh, you have a bag, okay. Yeah, on a blank sheet of paper, you don't need to put your name on it. I just want you to say one thing that you like about the course and one thing that you dislike or that you would change. All right? So one thing that you like and then one thing that you would change about the course. And while you're doing that, I'll hand back your quizzes. I will put the solutions up for the quiz today, and as you look at your numbers, remember the multiple choice counted more than 1 point, so I just marked off how many you missed on each page, and so you'll need to take that into account. I'm pretty sure there wasn't a curve. I'll have to look back and see. I'm pretty sure there wasn't.